Hi everyone, in this video I'm going to give you an overview of the lesson 3.4 braking distance. So for the first question you were to answer in the discussion board in Blackboard. Just write down what you think the different variables are that would affect the braking distance of a car. Remember, the braking distance is the amount of roadway the car needs in feet to come from the moment the brake is applied to when it comes to a complete stop. So we're going to take a look at the formula that's used for braking distance. You have the formula on the second page. So I want you to take a moment, if you haven't already, and read through the variables here and what they mean. And then I'll give you a description as well. So this formula looks complicated, but it really is just a bunch of very simple operations. So D stands for the braking distance, which is what we are looking for, and that is measured in feet. V naught, this V with that little 0, that's part of the variable itself. Again, we pronounce it V naught, like naughty. That is the initial velocity of the car. You could think of the velocity as the speed. So as you start to apply the brake, the speed of the car is going to change. It's going to slow down. But V naught is how fast you're going when you stepped on the brake. In the formula, that quantity is squared, so raised to the second power, so that velocity is multiplied by itself. In the denominator, we have 2 times lowercase g. Lowercase g is the acceleration due to gravity. In this lesson, it's a constant, 32.2 feet per second squared. In the parentheses, we have F plus capital G. F is the coefficient of friction between the tires and the roadway. So if you're driving on a sandy road or an icy road or a wet road, the friction will differ. So in the note, it says good tires on a good road provide a coefficient of friction about 0.8 to 0.85. And finally, we have capital G. Capital G is the roadway grade, and this is if you're going uphill, downhill, or on a flat surface. Do note that capital G and lowercase g are different variables altogether. Even though they're both G's, you can kind of just treat them as different symbols. Alright, but the operations are simple. So the velocity is squared, that is divided by what you get after you multiply 2 times lowercase g times the sum of f plus g. So the first thing you would have to do is add together f and g and multiply by lowercase g and 2. And that's what you're doing in question 3. Okay, so I have the formula here rewritten once again, so we can see how we would evaluate the formula. So we're just simplifying the formula. We are not given a velocity, so we're leaving that as V naught squared. The lowercase g is the acceleration due to gravity. That's going to be 32.2 always for this lesson. And then we're given the values for F and capital G, so I'm just going to write those in here. Now the order of operations here is addition in the denominator, so we're adding these together first, then we will multiply by 32.2 and by 2. The multiplication can be done in any order, so I did go ahead and multiply the 2 times the 32.2 first, as I added the quantities in the parentheses together. Finally, there's one more thing I can do to simplify. In the denominator, just multiply those values. And my formula is now D equals V naught squared over 54.74. Okay, and that is the value that you would put, or the formula that you would put in for question 3. So then for questions 4 and 5, we are going to use that simplified formula to see what happens when the speed doubles. So we're going to look at a speed of 50 miles per hour and then 100 miles per hour and see what happens to the braking distance. Alright, in order for me to use the formula though, I need to make some conversions. So in the formula, the velocity has to be measured in feet per second, but normally when we think about speeds, we think about it in terms of miles per hour. So we do need to make a conversion, and in order to go from miles per hour to feet per second, we need to use these conversions here. So we're going to start with our speed of 50 miles per hour, and I'm writing 50 miles per hour as a fraction. And I'm first going to change the distance from being measured in miles to being measured in feet. So I'm using the conversion 5,280 feet is equivalent to 1 mile. I'm setting that up so the fractions cancel, the units cancel, and then I'm going ahead and converting the time. This is the same kind of conversion that we did in lesson 3.2. Once all of my units cancel out, I can then multiply the numerators and then the denominators. So in the numerator, I have 264,000 feet, and in the denominator, 3,600 seconds. And I could go ahead and simplify that by just dividing the top by the bottom. And I'm rounding this, well, I've rounded it to the nearest tenth right now, 73.3 feet per second. You could round that also to the nearest whole number if you wanted when you make your calculation. So we could use 73 feet. Alright, so this is the value that's going to go into the formula. So I'm using, once again, the simplified version of the formula. V0 squared over 54.74, and I'm substituting V0 with 73. So I need to calculate 73 squared and then divide that by 54.74. Alright, so do 73 squared first. That gives me 5,329. And I'm dividing that by 54.74. And that gives me a braking distance of about 93 feet if I round to the nearest foot, nearest whole number. Alright, so that means if we were driving 50 miles per hour, we would need 93 feet in order to stop the vehicle. So we're going to do the same thing, except think about what the braking distance is when we're driving 100 miles per hour. So when we're driving 100 miles per hour, we're driving twice as fast. So you can go ahead and use the same method of converting 100 miles per hour to feet per second. But either way, we're doubling the speed. So whether we double the speed in miles per hour or in feet per second, we're still doubling. So we can take the feet per second and multiply that by 2. So 100 miles per hour should be equal to 146 feet per second. So now I'll use my braking distance formula again, plugging in the 146 for V0. I have to square that and then divide it by 54.74. The order of operations are the same, squaring first and then dividing. When I square 146, I have when I square 146 and then divide by 54.74, I end up with 389 feet. Alright, so now the next thing we want to do is make a comparison. So we want to see, did the braking distance double? So 389 is not twice as much as 93 is, it's more than that, and we can find out how much more by dividing. So if we divide these two braking distances, we get a value of about 4, which means that if we were to double our speed, we would need 4 times the roadway to stop the vehicle. Now what you should also do, even though it wasn't part of the lesson, is think about what happens if you were driving 150 miles per hour. So this way you can investigate what happens if we triple the speed. So I'll leave this up to you, but see what happens when you use 150 miles per hour. So triple your speed of 73 feet per second take that value, plug it into your braking distance formula, and see what happens to the braking distance. All right, and then finally, let me just give you the connections. All right, so here are your connections for lesson 3.4. So again, we started to look at formulas and equations in this lesson, and we're going to be working more with formulas, equations, and solving equations for the second half of Module 3. But the important thing that you should take away here is that generalizing relationships and rules are really one of the most powerful tools in mathematics. So when you make generalizations, that's giving you a lot of information about something. We use variables, expressions, and equations as tools that can help us to make those generalizations. Order of operations and properties define how to use the formulas, and knowing how to calculate a formula, knowing how to set up a formula will help us to define the relationship between the variables. In this lesson, you are investigating the relationship between the speed and the doubling and the distance, the braking distance. So we wanted to see what happens when we double the speed. The braking distance was quadrupled. That has something to do with the fact that the velocity is squared. So investigate what happens when we triple the speed. So take that 74 or 73 feet per second, multiply that by 3, use the braking distance formula again, and then make a comparison. Does the braking distance triple? Does it do something else?